Okay, second hour of Physics 1C for December 13th. Okay, now we're going to talk about pressure and momentum carried by or delivered by electromagnetic waves. So we'll say of EM waves. Okay. All right, so we had from above that the Poynting vector, which was intensity, was equal to it was EB over mu naught before we did the time average, right? And intensity is basically power divided by area, right? Your book has its own way of doing this derivation. I'm going to do a different version that I think is easier to understand. Suppose that I have a mirror right here. And say that we shine a light at it like a laser pointer or something like that. So we've got a laser pointer. We shine it at the mirror. There's going to be a wave of light, and it's going to come and it's going to hit the mirror. That wave will then, after hitting the mirror, be reflected back off of the mirror. Okay. And similar to the way in which if you were to take a bouncy ball and throw it up against a wall, it would bounce off the wall, and that ball would deliver a momentum to the wall. Even though you can't physically see the wall move, like you take a ball, you bounce it off the wall doesn't move, but you know that there's a force that's felt by the wall when that happens, even though the wall doesn't move. Well, it turns out that this wave, when it hits the mirror, it actually exerts a force in this direction on it. And we can calculate how much force it exerts, or at least the pressure that it produces, depending on how big the laser beam is, for example. Okay. And what we can do is we can say that from Physics 1a, we know that power is equal to the dot product of force times velocity. Or just in terms of magnitude, we can just say it's basically force times velocity, assuming that the force and velocity are parallel to each other, as they are in this case. So if we replace power in this equation right here, what we get is EB over mu naught, which, after all, this is the Poynting vector, by the way. So EB over mu naught. Are we going to use average, really? I'm not going to write this part here yet. We'll just say that's intensity. I'm comfortable with. I know for a fact that this is intensity, so we can work with that for now. So EB over mu naught is our intensity, and we replace P with force. We replace P with force times velocity. But what we're going to use in this case is, because the velocity is the speed of light, we're going to put C right here. And that's divided by A. And then in our equation right here, we also have F over A, force divided by area. Does anyone remember what that is? What's force over area? Pressure, that's right. So this is pressure. And the symbol your book uses for pressure, this is really, this is a weird thing to be talking about, because we're talking about power, pressure, and eventually we're going to talk about momentum. So I'm going to use capital P for pressure. Just, I apologize that it obviously looks a lot like, power. Right? This is power. And this is pressure. Okay. So that means that we can replace EB over mu naught. This is going to end up being pressure multiplied by the speed of light, but we can just divide the speed of light over here, right, on this side. And so now what we have is the intensity divided by the speed of light is equal to the pressure. And so there we go. This is what we call radiation pressure. And it tells us that light itself exerts pressure. In fact, our sun, it sends out light radiation in all directions. And that radiation actually pushes on particles that are in the solar system and kind of tends to push them out of the system. You can think about it as a type of like solar wind. It's not real wind, but it's like a solar wind that's kind of like pushing on all the particles, all the dust particles and stuff that are in our galaxy. And the sun is basically, not galaxy, sorry, in our solar system. And the sun is kind of sweeping. It's almost like the opposite of a vacuum cleaner, right? A vacuum cleaner like sucks things in. The sun is pushing out, and it basically exerts this type of radiation pressure on all the gas and dust particles in our solar system, and it effectively pushes them out of our solar system if they're small enough, if the pressure is big enough, right? Now, the way that it's the part where I get really confused here, because what they do is they do this in the other book that I use too, and I don't really fully understand it. They basically say let I be equal to S average. Then what happens is that your radiation pressure is equal to S average divided by C, which makes me wonder why we even wrote any of this stuff in here. Because S average is the one that's like E max, B max divided by 2 mu naught times C. So this is going to be our radiation pressure right here. And there's going to be two possibilities. When you have a situation like this, where the light comes in and it reflects off, so if you have pure reflection of a light wave, you're actually going to get extra pressure. The radiation pressure is going to be double this value. And if you have pure absorption, like if you have a dark black surface and you're shining light onto it, then the radiation pressure is going to be just P radiation this is going to be S average over C. And then if you have something that's like partial reflection or partial absorption, we'll say partial reflection, let's say. Maybe you have a body that absorbs 70% of the light. Let's say you have some fraction F that represents the fraction of light that is reflected by the body. So here, I'll put that on the second line to be more clear on what I'm saying. So let's say let F be equal to the percentage of light that's reflected by your surface. I think with something that's like very dark black, it's going to have 0% that's reflected. Something that's like a mirrored surface is going to have 100% reflected. And then other types of colors are going to be somewhere in between. So if you have like a green surface, some of it's going to be reflected and some will be resorbed. In this case, your radiation pressure for like the general form, I believe, is going to be something like 1 plus F times S average over C. So that's kind of like the general expression. And we have the problem we can do right here. Anyone have any questions about radiation pressure? So light can actually exert pressure. When you take a laser beam, like a laser pointer, and you shine it on a board, there's a certain amount of pressure that's put on that board. And the amount of pressure is however powerful the laser beam is, divided by the speed of light, and then multiplied by this. It's important to understand that this quantity is going to be a very small number most of the time. For example, if we looked at the radiation pressure from the sun on the surface of the Earth, we said that the pressure then would be equal to, let's say that the sun shines down and it hits the black asphalt of the road or something like this, and we want to look at the radiation pressure. So it's going to be pure absorption. If it hits asphalt, asphalt's very dark and absorbs most of the light that's incident upon it. So radiation pressure then would be something like 1400 watts per meter squared, and now you have to divide by the speed of light. This is why this radiation pressure is extremely small. What's this number going to be? Can you all... Oh, there's milk. Yeah, really tiny amount of pressure. 4.7 times 10 to the minus sixth, and the units for this are pascals or newtons per meter squared. If we want to compare that to in atmospheres, we would have to divide by 1.013 times. Basically, have to divide by 100,000. So in terms of atmospheres, this radiation pressure would be equal to 4.61 times 10 to the minus 11 atmospheres. If you're more comfortable with that version. So what does this tell you? This tells you that on our planet, the pressure of radiation is minuscule. Okay? It just straight up doesn't matter at all, because we're surrounded by an atmosphere that exerts a pressure that's 10 to the 11 times bigger than this, right? Approximately. We're like about whatever. You get the idea. So we're more likely to feel the pressure of our atmosphere than we are to feel the pressure of radiation. But we really don't even feel the pressure of our atmosphere, right? Because, our bodies are used to it, right? We're used to the fact that we're surrounded by one atmosphere of pressure. In fact, our ears detect when we sense changes in pressure, such that when you get into an airplane and you take off, you start to feel that pressure in your ears. Or if you get into a pool or the ocean and you swim down really deep, you start to feel the pressure. But there's no place on Earth you can go where the radiation pressure would be very high, right? In fact, even near the surface of the sun, this radiation pressure is probably not substantial. Imagine you're in a spaceship and you're flying next to the sun and you get relatively close to it, not so close to burn up your spaceship, but close enough that you want to feel the radiation pressure. You're not going to feel much because there's other forces that are at play that are greater than it, right? There's going to be the force of gravity drawing you into the sun. That's going to be significantly bigger than the force of the radiation pressure. So why do we even talk about this? Well, it turns out that we can use this to do things. So one thing that I've seen in more recent years that you can use this to do is you could use a ground-based, really powerful laser to drive a very tiny spaceship that carried very small amounts of cargo in space. And I've seen proposals for people to do this where they take small spaceships that have instruments that can collect data, so little tiny probes, right? The probes would be about the same size as like an iPhone. Okay, this isn't an iPhone, but the probes would be about the same size as an iPhone. And what you would do is you would shoot a laser beam from the Earth to give these objects energy from this radiation pressure, and you could use it to speed them up from the Earth. That means you can have a device that has no propulsion on it, or very, very little amounts of propulsion, and you could get it to go somewhere in space for you, which is really powerful, right? Other ideas that people have used this part we've actually done before. These are just proposals that people want to use lasers as a means of stellar transportation. Another possibility is you can use the energy coming from the sun to construct giant sails, what are called solar sails. I suspect some of you have probably heard of these before, right? Have any of you heard of solar sails? You have, okay. Anybody else? Yeah, okay. The idea is that what you do is you send a vessel up into space, right? You launch something off the surface of the Earth, right? Here's the Earth. You launch your object up into space. And then when it gets out into space, the spaceship has big unfolding sails, just like the way we use sails on ships to cross the ocean. And these sails, what happens is they expand and they're really big. And of course, you make them of a reflective substance, right? You want something to be reflective because of this factor right here, right? If it's reflective, you're going to get more energy. So you have this huge sail, and now what happens is that you've got the sun back here, and the sun is providing this stream of radiation, and that radiation provides pressure on your sails, right? And if the sail's big enough, right? If the sail happens to be large enough, it doesn't matter, for example, that the size of the radiation is small. Now, keep in mind that the size of the radiation in space is much larger than it would be on the Earth. But even if the radiation was this small, if you have something that gets this much radiation or this much radiation pressure, and you make it so that it's, let's say, 10 to the 6 meters in terms of size, which would mean, like, for example, if you make this side 1 kilometer and this side 1 kilometer, right? So 1 kilometer by 1 kilometer, and you have this reflective surface that's folded out here, maybe made of foil or something like that, right? Well, then you could get 4.6 newtons of pressure. And the cool thing is that the sun is never going to stop providing you that energy. One of the biggest problems in traveling in space is that you have to carry your fuel with you. If we want to send something up into space and then we want that spaceship to, let's say, go to Jupiter, we have to make sure that after the spaceship gets into orbit, it still has enough fuel left over to get to Jupiter, right? To change its orbit so it can get onto orbit with Jupiter. If you use solar sails, though, you have an inexhaustible source of energy, the sun, to provide you with the ability to manipulate and change your orbit. And we have proven by sending these things up into space that we can actually change the speed of these objects and change their orbits. It's slow, it takes time, but it doesn't cost any money, and it doesn't take any energy other than the energy that's provided by the sun. So it's a very promising way of providing the ability to kind of travel through the stars. It's just, one idea. Who knows? Maybe in the future we'll be able to make huge, gigantic sails and use them to accelerate ships to very high speeds, In principle, it's certainly possible. It's just an engineering problem of how can we construct a vessel that can carry with it a big 5 kilometer by 5 kilometer sail so that we can unfold it and nothing breaks, basically. And we can still harness all that energy. So it's a pretty cool idea, I think. All right, let's look at this problem right here. Power and pressure from sunlight. Okay. Oh, look, there it is in the textbook. They do mention this same number that I used here. In fact, they actually did this calculation. I didn't realize that before I did it. Okay. So, power and pressure from sunlight. An Earth-absorbing sunlight has solar energy collecting panels. So we've got some kind of sunlight up. Let me stop using yellow. I shouldn't be using yellow. Suppose that we have a satellite. It has solar panels. Big fat solar panels sticking out here. With a total area of 4 meters squared. So the area is 4 meters squared for the total area of the solar panels. It says, if the sun's radiation is perpendicular to the panels and completely absorbed. Well, that's kind of stupid because solar panels always reflect. Find the average solar power absorbed and the average radiation pressure force. Okay. I guess we're just going to be using that same 1400 because it's near the Earth, right? It's orbiting the Earth, right? Earth orbiting satellite. So we're still going to use that same pressure. So we have our pointing vector S average is going to be the intensity of the sun, 1400 watts per meter squared. We obviously have an area of 4 meters squared. It says that it's completely absorbed. So if we want to figure out the power absorbed, we just do intensity times area. So S average multiplied by area. So 1400 watt over meter squared multiplied by 4 meters squared. So we'll get, 28 times 256, 5600 watts. That's the power. And then find the average radiation pressure force. To get the radiation pressure, because it's fully absorbed, you just do S average and you divide by C. So you do 1400 hold up. It says radiation pressure force. So we also have to multiply by area. To get force, F, you need pressure times area. So radiation pressure is going to be S average over C times the area of our vessel. So 1400 times the area of 4 meters squared. So this is going to be 0.9 times 10 to the negative 5. Very small amount of force. And since this is a satellite, you would assume that wouldn't be enough force to kind of alter its orbit or anything like that. All right. That's radiation pressure. Anyone have any questions? So that is it. That's the end of chapter 32. We've covered everything. Now, if I think back to everything we've done this semester, I feel like we covered most of the things in the last 11 chapters. I know there were some things that we skipped from time to time. We definitely skipped some of the stuff about dielectric constants, and we didn't really talk too much about magnetic constants as well, and about how different types of magnetism or anything like that. But we covered pretty much everything. And in terms of what's going to actually show up on the final, that's what it is. It's basically going to be everything. So I said this at the beginning of class, but I'll just summarize now what you can expect to see on the final, so you can be prepared when you study, and then we'll be done a little bit earlier today. So for the final exam, I think it's important to understand kind of like what we've studied overall. So just to give a kind of summary of what we've studied. This semester can be broken down, I think, into 4 sections. And those 4 sections are electrostatics, electrodynamics, magnetism, and then of course the final part is the combination of electricity and magnetism, which is electromagnetism. You know, where you just make a new word and just mix them together. So for electrostatics, what we learned was things like electric potential. Mostly these kind of problems are handled usually most easily with Gauss's law, although you can't always do that. So sometimes you have to do things like use the idea that the size of the electric field can be given by this expression. But we also learned about things like electric potential. We learned about the electric potential of a point charge, which is K times the size of the charge divided by the distance away from the charge. Make sure you still remember how to do electric field and potential calculations. We also talked about things like electric potential energy. What else shows up in this? Also capacitors. So we learned about capacitors and the way in which they can store energy and charge, where the amount of charge that they store, Q, is equal to the capacitance times delta V. And then, of course, we have some energy expressions here for these, which are like Q squared over 2C. And, we have, there's other equations that show up in this area, but the big ideas are Gauss's law, electric fields, potential, and then what capacitors do, how they combine, how they hold charge, and all that kind of stuff, right? And then I guess, there's other equations that show up in here, but I'm not going to write down every single equation, just to say that electrostatics is the study of electric charges while they are at rest, while they're not moving. And these are all examples of things that came out of that. The capacitor, electric potential, electric fields, Gauss's law, right? Definitely need to understand all of these concepts because there very likely will be some kind of a problem from this chapter. The second section of the textbook and of this course is where we start to talk about the way in which electricity works whenever charges move. And in this particular section, this tends to be charges... That's not true. I was going to say constant velocity, but it's not true because we talked about RC circuits too. Largely, in this section, we're talking about electricity where the electric charges are moving with a constant velocity. And in this, we learned about things like electric current and the way it was related to something called drift velocity. Something like this. I think that's the right equation, right? And we learned about the way in which electric potential is related to current and resistance through Ohm's law. We then learned about what a resistor was and how you can combine different resistors together in circuits, the way in which those resistors can combine in series or in parallel, similar to capacitors, and then how you figure out how the charges split up at junctions, which is what's known as the Junction Rule or Kirchhoff's laws. I'll just write Kirchhoff's laws because that's one of the big kind of parts of this. Make sure that you review those and understand the sign conventions that we use in case I give you a resistor problem of some type. But also just because Kirchhoff's laws are just in general very useful. What else did we talk about with electrodynamics? We talked about the way you define resistance, right? That resistance is equal to resistivity times the length of the wire divided by the area of the wire. What else did we talk about with electrodynamics? This is the shortest section for sure. I'm going to go back to the table of contents in your textbook and make sure that I'm not missing anything here. I feel like I am. Nope. Okay, I got everything for the first half. Current, resistance, resistivity, EMF. Oh, I guess that's another one. Power is equal to current times change in voltage. So we get that connection with energy. And then, RC circuits. Understanding how to find the time constant for those. I know, I think on the last final that I gave, was it a final or was someone asked me a question? No, it was one of the homework problems. I think Justin asked me this question about where you have like an RC circuit and it's inducing a current in another loop. So there's ways in which the RC circuit could show up in that way, which would be a lot. What else is there? That's it. So then we go into magnetism. And in magnetism, what we learn here is that electric currents tend to have magnetic fields around them. And we learned how you can calculate the magnetic force on a particle. This is sometimes referred to as the Lorentz force, that the magnetic force on a particle is Q times V cross B. And we also learned about the magnetic force that's created on current-carrying wires, the equation where it's I times L cross B. Learned about the torque that's put on a current-carrying loop, where you have this mu cross B thing, where mu is the magnetic moment of a loop, and it's equal to N times I times A. The area of the loop times the current flowing through the loop multiplied by the number of turns. And when you place a loop of wire that has current inside of it into a magnetic field, it'll feel a torque according to that equation. Motion of charged particles in magnetic fields. And then after learning about all the ways in which charged particles and currents are affected by magnetic fields, the next thing we learned is how to produce magnetic fields via things like Ampere's law, right? Where you can use the B dot dl. Be careful about this. Equal to mu naught I enclosed. I noticed that a lot of mistakes, I'm not trying to call anyone out in particular because so many people made this mistake that I think it's more related to probably me and the way that I taught you all this stuff. Be careful about using this equation. We derived specific solutions to this equation so that you don't really have to use it very often, right? We looked at the line of charge at some point, a distance r away, and we said that the magnetic field, if you have a current flowing here, was equal to mu naught times I over 2 pi r. I know on the last exam I saw a lot of people trying to use this equation to solve problems where you already were supposed to kind of know that you can just use this. You don't need to rederive this. You can just use this equation, right? Particular, I'm thinking about the problem where you had this this right triangle, and there was a current here, and there was a current here, and you were supposed to find the magnetic field at this location. I guess this reminds me, one of the things that you need to know for the final is how to use the right-hand rule. I know this is tricky, but this problem on the last test, if you want to find the magnetic field at this location, what you have to do is you have to point your thumb into the page, and then you kind of like sweep your fingers in the direction of the magnetic field, and it creates a circular magnetic field that kind of goes around like this. So at this location right here, the direction of the magnetic field vector is this way for the bottom one. Let's say we call that one B1. Call this one 2. And the direction of the magnetic field at this location for this one is this way, B2. So tons of people got this wrong, and I know a lot of this is because it's really hard to communicate this like hand motion stuff when I'm sitting here and you're sitting across the screen. Probably, no offense, not paying attention, because it's hard to pay attention for as long as these classes are. That's all I'm saying. So it's very difficult to learn this stuff. If you got this wrong on the last test, definitely make sure you understand how to find these kind of vectors, okay? And that also goes for when you're finding these electric field vectors, because another kind of problem, I'm not saying this will be on the exam, but it might be. You know, on the first test, we had this kind of problem where you had like 3 charges like this, and you had to find the electric field at this point. So keep in mind the fact that if I have a positive charge and I come to here, the electric field vector goes this way. For a negative charge, the electric field goes this way. And for this positive charge, the electric field goes this way. You need to remember all those kind of conventions that we have in order to be able to solve some of the problems they're going to show on the test. Anyway, so like on this problem, for example, I had a lot of people that would write this equation down, and they didn't really seem to understand how to use it. So if you don't know how to use the equation, don't use it. It's not a problem. Just you know that the electric field created by a long current carrying wire is this. You just use that equation. Similarly, we also figured out that you can define the electric field of a ring. So if I have a ring that has n turns and it has like a radius a, for example, for this object, the magnetic field at the center, not at other points, is mu naught I divided by 2a. And if you have multiple rings that are like, you know, wrapped on top of each other, you multiply by n right here. And then the direction of the magnetic field is given by the right-hand rule. What else? So that's sources of magnetism. We also learned about the Biot-Savart law. I'm not going to write that down. We learned about magnetic flux, blah, blah, blah. The force between parallel conductors, and Ampere's law. Yeah, so that covers everything. Okay. Finally, with electromagnetism, we learned about the concepts of things like induction and using Faraday's law of induction, which is negative n d phi dt, and Lenz's law to figure out how much EMF would be generated in a system. And then from that, we learned about, you know, how to calculate flux, magnetic flux in different situations. We learned about Lenz's law. We learned about induced electric fields, where basically we make this equal to integral of E dot dl. And then we solve for the electric fields. There's not going to be much else from this chapter. Yeah, that's it. So we use this equation to solve for, you know, when you have changing fluxes, that's going to produce an EMF. And then the next thing after this is to talk about something called an inductor, where for an inductor, the EMF is negative L di dt, and we learned that you can calculate, I'm kind of running out of room over there, you can calculate the inductance by using this expression, n phi b over I. Flux. Yeah, I mean, you know, Gauss's law, right? We know that flux is equal to, sorry, phi E is, I'll erase that. Flux is integral E dot dA, that kind of stuff. And obviously magnetic flux shows up down here. We learned about back EMF. We learned about, what else did we learn with inductance? We learned about transformers. Oh yeah, and then the other types of circuits. We had the LC circuit with the oscillations. We had the LR circuit with decay. And then finally the RLC circuit, which we then looked at in, these are all DC. But eventually we looked at AC circuits, which led to learning about impedance. This idea, the square root of R squared plus XL minus XC. And of course you have to remember what XL and XC are. Well, I send you the formula sheet. When I've got it done, I'll put it up. I'm probably going to write the exam tomorrow. Well, I have a lot of it written, but I'll put the whole thing together tomorrow, and I'll try to post it on Canvas. It's pretty much going to be the same equation sheet from the last exam, but I'm going to add on some of these latter equations here, right, from the AC chapter. Yeah, so we learned about alternating current and how that works. Hopefully you've studied that, you understand it, and that pretty much covers everything we did this semester. You know, that's pretty much it. For electrostatics, Gauss's law. For electrodynamics, I guess the big equation is Ohm's law. For magnetism, this is the big equation for finding magnetic fields. And then for electromagnetism, this is the equation, really this equation is the equation, I can't box it in anymore, that relates everything together. No, there's going to be 6 problems on this test, Johnny. Yeah, there'll be EM wave problems. I'm not including this on this list right here. Sorry. In addition, there's also going to be problems on EM waves, right? So in addition to all of this, there's also plus some EM wave problem. EM waves, radiation pressure, Poynting vector. All the stuff that we did today is also fair game for the test. I just didn't repeat it, but that's a good question, so I appreciate you saying that. Yeah, so 6 total problems. I could write this stuff. I don't have to... I have to assume that commonly when I'm talking, you're not hearing me. So 6 problems, not due any fault of your own, but because, it's hard to pay attention. It's hard to hear everything I say. I talk fast, and quite commonly the internet may be garbling up what I'm saying. So 6 problems, all this stuff. It's overwhelming, Tom Bui. I'm sure you'll be fine. You've done pretty well so far. It is overwhelming, though. I agree. You're right. It's a lot of stuff. And I'm really reluctant even to write down all these equations as I'm talking about this stuff, but I'm just trying to categorize the kind of things that you need to understand to be able to solve problems on the final, right? You need to understand what all these equations mean. Ideally, you need to be able to say them in words, right? You need to be able to, for example, look at this equation right here and say, this tells us that we find electric field by taking little tiny point charges, dividing by the distance away squared. That one's easy, right? But you also need to be able to describe other types of equations that show up here. Like, what does this equation say? And what does this equation say? This equation says that when you have a changing flux, it's going to produce an electric field. The electric field is going to be circular in nature due to the fact that you have a circular integral that you're doing, a line integral. And, you just need to be able to do your best. That's the biggest thing. There's going to be 6 problems. I'm only going to grade 4 of them, so I'm going to drop 2. So the biggest thing is, when you get the final, figure out really quickly the 2 problems. There's probably going to be at least 2, hopefully, that you understand how to solve. You should solve those as fast as you can. And check over them, make sure you get them right. When you get a problem completely right, it goes so far to helping your grade. So if there are any problems on the final that you immediately acknowledge that you know how to do it, you should immediately solve it, right? And then find out what other problems are a little bit less difficult for you, or a little bit more difficult, I should say, and then try to solve those. And then just go from there. Just, solve what you can. Don't waste a lot of your time. And then you should be fine. You have 3 hours. You only have to solve 4 of the problems. Is there a chance that I will grade your labs before Wednesday? I don't want to lie to you and tell you yes. I will try, but I'm not going to promise anything. Why does it matter? Does it matter if you get the labs back before Wednesday? Is it because you want to know what your total grade is going to be before Wednesday? If you turn the lab in, okay? If you turn the lab in, you can assume that you're probably going to get a decent score, okay? As long as you didn't make egregious errors and leave things off, right? So if you feel like you did the lab properly and you reported your results correctly, the lowest grade you would get, if for whatever reason there was something wrong, was probably an 80%. If there's a lot of things missing, you get a lower grade. But as long as you filled in all the boxes, you did all the right stuff, and you came up with answers, and you have errors on everything, like absolute errors, percent errors, all that kind of stuff, you don't have anything to worry about, You don't have anything to worry about. So just go ahead and assume, as far as your final grade is concerned, that those that whatever your current lab average is, just assume that it's not going to change, Kavi, okay? Because it probably won't change a lot. Use that as your baseline for calculating, what you need to get on the final. Regardless, this is something that I'm going to say that's probably, I don't know, this would probably piss a lot of people off. It doesn't matter at all what grades you need to get on the final. What matters is how well do you know this stuff, So I know that students in general, and I mean, I did this when I was a kid too, like you want to figure out exactly like what's the minimum grade I need to get to pass the class, right? But it's just the wrong way to think about education. I mean, it's one way to think about it, but in my opinion, this is only my opinion, it's the wrong way. And I think the right way is you just want to learn the material as best you can. You want to go into the final exam armed with all of the different understandings that you've gained over the semester and use those to perform as well as you can. And it doesn't matter like what the grade you need to aim for is, because it's almost impossible to know, like, as you're taking a test, especially the way my tests are written, where, like, each problem is 25 points, but you don't fully understand how the points break down. So it's very difficult to know while you're doing the problems how good of a grade you're going to get, right? Because, like, let's say you answered every part to every problem correctly except for one. You don't really know how much that part's worth because I don't tell you to begin with, which, you know, I think some people would say I should do, but I really don't like doing that because I think it gets you thinking in the wrong mindset. The right mindset is try to understand this stuff as best you can. You're probably, if there's any bits of this stuff that you don't know by now, it's going to be very hard in 2 days to learn all of it, right? So a better thing to do is to focus on what you do know, right? So we have 10 homework assignments, I think, maybe 11 homework assignments. What you really want to do is, if you can master something like 8 out of 11 of those assignments, let's say, for example. Let's say that you know for 8 out of those 11 assignments, you can take the time in the next couple days and you can do every single problem or the majority of them and you can nail them, right? Then you're going to be doing really well in the exam, right? If you can find time to go back and do all of the homeworks again, and you know how to solve every single one of them, then you should expect you're going to get a 90% plus on the final, right? If you can solve every single homework problem and you know how to do it and you don't need help from anyone, you should expect you're probably going to get a 90% plus on the final, okay? This also includes lab annual homework, by the way. You definitely need to be able to understand how to do the lab annual homework too. But if there just isn't enough time for you to do that because you have to study for other exams, then instead what you should do is to focus on what you're good at, right? Maybe you were doing really well in the class for the first two sections. You didn't really understand this one, but then you did a little bit better in this last section, let's say, for example. It would be well worth your while to go back and put a little more time into the things that you know well to refresh your brain so that when you get to the exam, you guarantee that when you see a problem, like maybe a problem like this or a problem like this, that you know what to do and you get 100% on that problem. Because if you get 25 out of 25 on a problem, it really just boosts your grade. It really helps it make it more likely that you're going to pass, right? So don't worry about what the numbers are. Worry about studying the material, study the homework problems and how to solve them. And that's the best way you're going to succeed, I would say. Anyway, I hope you all pass. I hope you all do well in the final. I know it will be overwhelming. I know it'll be hard, but the biggest thing to mention is that it probably won't affect your grade that much. You can go into Canvas and plug numbers in. You'll find out that it's not really going to alter your grade very much. So you should really come in with a nothing to lose mentality, everything to gain. Is it going to be like exam 3? I don't know what that means. What do you mean? So hard. Yeah, it's probably going to be hard, Coffee. But I have to say, I don't think exam 3 was particularly hard. And I know for a fact it could have been harder because I've given harder exams in the past. So, yeah, I mean, it's E&M. It's Physics 1C. This class is notoriously very difficult, and the final will be difficult. But, you know, it is what it is. It's just one of those. This is just one of those things you got to do. You got to get through this class, and you do your best, and you know, maybe you won't perform as well as you want to on the final, but there's so many other ways to get points in this class that you're probably going to be okay. Almost everybody. I haven't looked at the grades recently, but I know that everybody has a chance. I know that everybody has at least a chance of passing at this point, and if you didn't, you probably already dropped the class. So, you know, just don't worry about it. I think I did say, didn't I say to you all in the last lab that, oh boy, I hate saying this right before a final, because this could really lead to people slacking off. I'm pretty sure I said that since the exam average for exam 3 was so low that, and I know the exam average for exam 1 was pretty low too, I said that there's some possibility that I move the grading scale to make it easier to get a B or easier to get a C. I probably won't change the mark for an A unless nobody gets an A, but I know that's not going to happen because some of you are really good at this stuff. So I probably won't change the mark for like 88% to get an A, but I may lower the C to like 75%, for example, and I may lower D to like 63%. Not by a lot. I'm not going to change it by a lot. I'm just saying, like, this is why you really shouldn't go into the final thinking about what you need to get a certain mark, because I may lower the marks. You know what I'm saying? I'm not going to raise them. I'm not going to make the grading scale any harder than it is, but I might lower them. Now, I don't think you should assume that I'm going to do that. I don't want any of you to ask me at the end of class if I did that or not. You'll know when you get your grade. You know what I mean? It's really none of your business if I decide to do that or not, because it's based on my assessment of the entire class as a whole and their performance in the online environment of this like COVID thing, right? If I determine that it's worthwhile to lower the grade so that people that I think deserve to pass should pass, or if large numbers of people are failing, I'll do it, okay? So this goes back to, don't worry about what your grade is going in. Just look at this as an opportunity. That's what an exam is. It's an opportunity for you to show me what you've learned and to try to get as many points as you possibly can to help to, help your grade out. That's what it is. It's an opportunity. And I know it's stressful, and I know that when you show up that your brain isn't going to work right and all that kind of stuff, but it is an opportunity and you have nothing to lose. Because by the time you get into that room and you take that exam, it's just all about how many points can you get, and it's just a race to see how many points you can get on that test in that limited amount of time. So make sure you sleep well, make sure you study well. Masks give you headaches when you take the exam or lab. Yeah, me too, man. I don't know what to tell you, dude. It's tough. It's tough. You can, Johnny, if you want to. Haiti, if during the exam we're turning off, we're gonna stop right there and I'll start talking and make sure that none of this stuff is recorded.